Hello, my friends. Welcome to Origins. My name's Don Chapman. It's so good having you with us today. You know, Origins is a forum where we take the evidence of science and we use it to validate the truth of creation. And today we have a very exceptional guest with us. We're very honored to have Dr. Stephen Austin with us. It's great to have you here today.
Thank you, Don. I
feel like it's almost amazing that we got you out of the dirt to come and be on the show. It's great to have you.
It's good to be here to share these things with you.
We're excited to have you. And today we're going to talk about a term that I'm not sure I ever heard until you used it, continental sprint. Can you tell us what that is?
You've heard of continental drift?
Yes, sir.
There was a German meteorologist almost exactly 100 years ago who published a book on the origin of continents and ocean basins. His name was Alfred Wegener, the German meteorologist. It was a book on continental drift. And he believed that the ocean basins formed by a supercontinent split apart, moving very slowly over hundreds of millions of years.
So that would be part of the whole uniformitarianism, that everything had to have slowly and gradually at a uniform pace.
Yeah, and Alfred Wegener's theory of continental drift was rejected by geologic establishment because he was a meteorologist and he had this idea that the ocean basins form very slowly by the continents moving apart. He got the idea from a Christian creation catastrophist named Antonio Snyder. And so we want to go back and honor a pioneer of science, and we can call his theory continental sprint. And his idea was that continents didn't drift slowly, they move fast at a walking pace, something like that, so sprint.
It's going to be a fascinating show to talk about that. Now, for our scientists out there, what's CPT?
CPT is the other name for this. We call it continental sprint, but it's really catastrophic plate tectonics. If you want to talk to scientists, you got to use science terms.
Yes, sir.
And so catastrophic plate tectonics. And plate tectonics is the idea that the Earth has been deformed, the Earth's crust, on the boundaries of giant plates, and these plates crashing against one another, sliding by one another, creeping underneath one another. Those are the processes that form mountains and ocean basins and ultimately the continents and the seafloor.
Well, now we're going to talk today about what the world was like after the continental sprint. Is that right?
That's right. Well, continental sprint didn't all of a sudden stop. There's some leftover effects and after effects. And tectonics continued. The process that deformed the Earth continued into the present day. And of course we have earthquakes and we have volcanoes today and things that remind us of tectonics, but nothing like the tectonics of the past. We have volcanoes to talk about. We have the sedimentary process, what was going on during the flood compared to what was going on now after the flood. And erosion. And erosion continued. And some big canyons and things opened up. And then, of course, the Earth cooled off, and so we had global cooling since the continental sprint. And so we have a lot to talk about here.
We sure do. And I'm going to be interested to hear about global cooling because we hear a lot about global warming.
I've drawn a graph here showing the intensity on the vertical axis and time on the horizontal axis from the end of the flood to the present. Okay. And as we draw this graph, the graph of everything declines with time. And it's an exponential curve, if you know what I mean. In other words, things dropped off very rapidly to begin with and now have kind of flattened out in the present day. And so the geologic intensity of tectonics, of volcanoes, of earthquakes, just all geologic process seems to follow the curve like this. So we had catastrophic plate tectonics, or continental sprint back there, the time of the flood, and then the world has recovered. We went through an ice age, a big ice advance and an ice age.
Ice age was a natural consequence of the flood, wasn't it?
Yes, yes. Let's talk about the tectonics associated with the slowing of continental sprint. Now, horizontal plate tectonics was occurring during Noah's flood. and thousands of kilometers of displacement of seafloor and continental plates occurred. Today, that process is largely stopped. We're seeing some leftover residuals from it, but what happened is vertical tectonics took over. And that's what I'm trying to show here on this graphic, is the edges of a continent were a collision belt between ocean floor and the continental mass. What's happened since this flood? We've had a lot of vertical tectonics, up and down, unloading and loading due to movement of things around, underplating where things have been shoved under and things are rising up. And so up and down motions largely dominate in the present world.
Okay.
So vertical tectonics and what's called isostasy, that's the principle of equal pressures at depth. And it creates this vertical tectonic world that we largely live in. And of course, as we look around, we can see the evidence of vertical tectonics. Like in the Grand Canyon, there's a sandstone layer that comes along like this, and then you see it goes vertical, goes straight up, and then it goes horizontal again. These layers do these bends, and that's showing us the upheavals that occurred. We've talked about tectonics. Now let's talk about volcanoes and magma that's down there in the earth. There was a lot of magma or molten rock that was resident in the mantle and the crust of the earth, and it's worked its way up to the surface. And of course, we have a wide variety of volcanoes. And we have small, normal stratovolcanoes, like composite volcanoes. We have giant volcanoes like caldera eruptions. We have dikes. We have underground structures where molten material has been intruded to form a variety of things, dikes and sills. And so this is the world, the volcanic world we live in. And we see these features all around us. For example, looking down on the Andes Mountains in Chile, we see a large mass of molten rock that has cooled to make the rock called granite. And this granite is very obvious in mountain ranges all around us. And so magmas have moved in under mountains and squeezed up into making mountains. And when magma breaks the surface of the earth, of course, it makes big volcanoes. Yellowstone is a giant supervolcano. I can draw roughly the outline of the collapse feature, but there's this enormous feature that comes around like this, an elliptical depression, something like 45 miles long, something like that. It is a huge depression, and most of Yellowstone, or half of Yellowstone National Park, is this giant collapse feature from the explosion of the volcano. So imagine the volcano was sitting here with a giant magma body underneath it. It was exploded along a ring, and there was an elliptical curtain of magma that was ejected as a supervolcano unzipped, and then this thing collapsed into the hole. Perhaps hundreds of cubic miles of magma was ejected in a single volcanic event. So there's nothing like that type of volcano today. And so we're looking at supervolcanoes in the past, and we're talking about normal volcanoes in the present. So Yellowstone is a gigantic volcanic collapse feature from a supervolcano. And as we look around, we see the volcanic ash deposits from the supervolcanoes. Like here in eastern Oregon, you can see the volcanic ash beds, and you can see lava flow layers thousands of feet thick. So lava floods and giant explosive volcanic eruptions subsided to make the present. And river deltas. River deltas are interesting. This is the Nile River Delta from space, and you can see where the Nile River comes down and into the Mediterranean, and this delta has formed largely since the catastrophic plate tectonics associated with the flood. Now, geologists are very interested in river deltas and what goes on underneath river deltas because they can be prospected for oil. And here is a kind of a profile that was made through the Mississippi River Delta. And you can see the very thick strata layers that are down there, maybe 5,000 or 10,000 feet down. And so the Mississippi River Delta is very deep. And a lot of material washed out there. And then it's kind of slowed down to the present Mississippi River. And so large quantities of sediment, especially in deltas, were deposited in the post-flood period after catastrophic plate tectonics associated with continental sprint. So we have large amounts of sedimentation, and we have large amounts of erosion. This is a canyon called Palouse River Gorge in southeastern Washington state. Palouse River Gorge has the Palouse River flowing through it. This gorge is about 6 miles long, several hundred feet wide, 400 feet deep. And it was eroded, we believe, by a gigantic glacier lake that breached its dam and flooded through here. A super flood or a mega flood came down through here and eroded a waterfall, and the waterfall cut back through and made this canyon. Catastrophic water flooding is one of the major causes for canyons like this. Even Grand Canyon, other canyons, can be explained this way. Grand Canyon is 4 to 18 miles wide, a mile deep, and 260 miles long. And off to the eastern side of Grand Canyon is evidence of a lake over here, a big lake. It's been called Hopi Lake, and it's about 6,000 feet elevation up against the elevated terrain in the north rim of Grand Canyon, which is about 7,000 or 8,000 feet above sea level. So a lake associated with an upwarp structure suggesting that Grand Canyon is a breached dam. Most people have junked the idea that Colorado River cut Grand Canyon. Most geologists recognize there's not an evidence of a through-flowing river for 100 million years by looking off for the delta for it. It doesn't exist out there. Instead, we got to explain it by some type of catastrophic event. And so in the post-flood period, there were big lakes. These big lakes drained, and they created the river systems, like the Colorado River. Here's a model how the Colorado River could have been positioned through the Kaibab upwarp to form the Grand Canyon. You see the Kaibab upwarp looking a little bit to the east. You see Hopi Lake at about 6,000 feet elevation. The lake is up against the upwarp and probably failed by water flowing through the dam and the dam collapsing. But it's a collapsed dam that notched the spillway through the Kaibab upwarp. And when that dam failed, then the next dam in the next lake, Canyonlands area up in Utah, that dam failed, and so a series or a multiple.
It's like domino effect.
A domino effect
and then
of failed lakes.
And that just kept the erosion going.
Yeah.
Made it happen. Okay.
And so the Colorado River is trapped in the canyon formed by the drainage of the lakes. That's an interesting way to think.
Yes, sir.
And post-flood climate, the evidence of exponential cooling of the oceans. Let's talk about the leftover heat from the global flood and all that tectonics on the seafloor. That heat that created the new ocean crust on essentially a large part of the planet, 70% of the planet was resurfaced. The energy that was released from the formation of that new ocean floor had to go through the atmosphere eventually. And so it's caused the cooling. What are the two things you need to have an ice age? You need cold, of course.
To make ice, but you also need heat, don't you?
You need heat to make an ice age, to evaporate water, to make snow, to be ice. So a rapid post-flood climate change and the exponential cooling could create the ice age. Increased rain and snow just after the flood because of the increased evaporation, because of the hot oceans to start with. The oceans are going to cool. And then the onset of glaciation. So it can explain a number of things. And then, of course, we lead to the present Earth, which is increased aridity. We have big deserts today, centuries after the flood. So the post-flood climate has been radically altered by going from the immediate post-flood world with the hot ocean to the present
Temperature of
climate.
the ocean has changed a lot of things on the Earth.
It did. And the cooling of the ocean generated a rapid post-flood ice age. Here's a model of data that suggests the Arctic Ocean cooled from maybe 20 degrees centigrade to essentially freezing today. Okay, and if that happened, yeah, that's a remarkable cooling. A whole ocean essentially cooled off by 20 degrees. That would create wild weather. We're thinking about increased precipitation after the flood. And here's a model that's been made. Here you see the continents, North America, South America. There's Asia over there and Europe. And as we begin with that situation and allow the Earth to cool with a hot ocean, it leads to increased precipitation. And you can see high areas of precipitation, like up in the polar areas and along Greenland and across some parts of Asia. And that could lead the rain, of course, leading eventually to snow. So we can imagine the global circulation at ice age max. But when the ice age and ice sheet was fully formed, there was ice over a large part of Canada, large part of northeastern United States, and over Europe and Asia as well. And this transformed the planet. And of course, these big glaciers left their imprint. Even Yosemite Valley in California was a giant glacier that came down through this valley, cut the granite and made the U-shaped valley.
Tremendous force in those glaciers.
And those glaciers are powerful post-flood erosion agents.
Yeah.
And then I like to think of the blast zone at Mount St. Helens and all the new organisms that are out there. But think about the animals and plants after the flood. They've got to distribute widely. And organisms are rather versatile at adapting to new habitats. And so here's the elk at the blast zone at Mount St. Helens having a wonderful time eating the grass out there in that formerly devastated area by the explosion of Mount St. Helens in 1980.
It's good to see it's back.
Yeah, and the elk and the plants and everything are back, and the ecosystem is recovered. Yeah. And so you imagine what was happening after Noah's flood. And then I think of the deserts today. We have modern big deserts like the Sahara, for example. But the Sahara underneath it has a lake. So a lake was transformed into one of the biggest deserts on Earth. That's amazing. So the worldwide global climate change and the formation of the arid deserts like in the southwestern United States with the rather small Colorado River sitting there in it.
Well, we got to take a break and then we'll come to these conclusions. But certainly when the flood was over, it wasn't really over. There was a whole lot of things still happening, and we've been looking at the effect of those and where we are today. So we want to wrap this up. We want to put some application to what you've shared with us. But before we do that, we have to take a break. Don't you go away. We'll be right back.
Today's guest on Origins, Dr. Steve Austin, is a field research geologist with his PhD in sedimentary geology. He is senior research scientist with the Institute for Creation Research. He has been involved in geologic exploration for 40 years on 6 of the 7 continents of the world. Steve has also done extensive field research at the Grand Canyon and Mount St. Helens. He is the author of several books, videos, and more than 30 technical geology papers. One of his books, Footprints in the Ash, deals with the 1980 eruption of Mount St. Helens. Dr. Austin can be reached at Institute for Creation Research, 1806 Royal Lane, Dallas, Texas, 75229.
We're back with Dr. Steve Austin. Dr. Austin, this is the wrapping up of 3 shows on Continental Sprint. And, you know, I've learned so much, and it makes sense out of so many things. Can you kind of wrap it together and just kind of give us a list of things that make more sense, things that kind of come into light when we understand what was going on?
We've been talking about how the Earth's surface has been deformed, how continents and ocean basins formed. We've been talking about what happened to the ocean during catastrophic plate tectonics, during this time of continental sprint, if you will. It is amazing to think about all the things that continental sprint and this idea of catastrophic plate tectonics, what it integrates. And so I've made a kind of a list of the model with explanatory power, catastrophic plate tectonics. I put some things on the list here. Mechanism, focal earthquakes, the earthquake focal mechanisms, earthquake distribution in the world. They're explained by catastrophic plate tectonics and normal plate tectonics as well. The way faults and faults move things, the thrust and detachment mechanism, better explained by catastrophic plate tectonics. The way the magnetic field reads in the earth and in lava flows, and the magnetic striping on the seafloor, and the magnetic reversals that are found, evidence of found in the rocks, argue that there was a rapid reversal of the Earth's magnetic field. The continent shapes and how they fit together, and the ocean bottom topography, and the ridges parallel to the continental margins, and things about the composition of the mantle. All of that makes a very cogent argument for rapid tectonics. We see high and low pressure temperature minerals that argue for high pressure during impact, even melted rock. And the way that the Earth changed after the global flood and the leftover heat, how it modified the climate, is very important. And so just the way climate changed and the way deposition occurred after the flood, thick wedges of deposits and big river deltas, and of course volcanic eruption deposits like lava flood layers like the Columbia River basalts in the northwestern United States, and the way diamond-bearing kimberlites are formed. And just a number of biblical issues like where the waters of the flood went to, what's the fountains of the deep, a number of questions like this tell us that continental sprint and catastrophic plate tectonics are very strong explanation that has a lot of explanatory power.
It's quite a list you've got there. And it's amazing to me when I read the story of Noah's flood in the Bible to think of all the science that's beneath the surface of that story and what was going on the earth and under the earth at that time. But it all makes sense when you put it together and talk to us, and we come up with a list like that of things that make sense when we understand the science behind the story of the flood. That's an incredible list. You have done us a great service. Thank you so much, my friend. It's been a joy being with you, looking at Continental Sprint. I'll never read the story of Noah again the same, There's so many images and pictures and knowledge that you've added to my repertoire. I'm very grateful. You know, God's Word's true, and the more we look into science, the more we discover the truth of God's Word. And we are so blessed as a church to have men like Dr. Steve Austin who help make sense of the science that validates the Word of God. Remember this, my friend, it's God's view that He created you. That should be your worldview too. Hope to see you again here soon on Origins. Until then, God bless you, my friend. Thank you, sir.
Thank you for watching this edition of Origins. To get a copy of the information presented today, you can download a PDF file of program number 1116 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins, program number 1116, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.